in unit of time. And these three lines, which you have over there, show you an average of 10. These three lines show an average of 10. These three lines show an average of 10. This one with a very large number of 10.01, 9.99, but 1/500 in middle of it is still kind of an average of 10 if you get it measured through the database in practice. Actually, people in theory would say they're actually equal to 10. That's the definition of real numbers. But us as humans, and the first person who told me that is Carrie Millsap, we actually react to not the average, we react to the difference between the average and what we experiment. So if you have an application which is usually fast, responds in less than, let's say, half a second. So your web application is responding in less than half a second all of the time. You find it a nice application. And then once upon a time, you get an answer which is 2 seconds. It's not a big difference, and by many standards, actually, it's still a good web application. You'll find that the application is actually not very consistent, not nice to use in general. And it can get worse. If the application, and I made this small calculation, if you actually have an application which has to do quite a number of statements, and at some point, for different reasons we'll look at in a second, it happens that your IOs are suddenly slower, then you'll see a big difference. Maybe something like 10 seconds, and then some people probably will call their desk, say this application doesn't work, I don't want to use it anymore, please provide something which is actually consistent. So if your application is responding in 0.5 second time, you'll be happy. If the application is actually responding within 1 second, you'll probably be happy as long as it doesn't change over time. So it's not an application which is 0.5 seconds, and then 1 hour later, for some 1 page out of 10, you get a 5 second response time, or maybe a 10-second response time, maybe a 1 minute response time. I think people say that usually after 7 seconds, on the web, people go. If your application has not answered within 7 seconds, people just quit, go to a different website. So imagine your application has to do 50 IOs, then it doesn't take a long time for a few of these IOs to actually reach these 7 seconds. And the worst is that it happens. And what I wanted to tell you in this short talk is actually probably you don't know, if you don't look at it, that you have these long IOs, but your users know about it. And if you would ask them, or if they complain to you, you will know. But what you can do is proactively gather information about it, and then be able to analyze it, understand it, and hopefully fix it. So it's all about pathological cases of latency. A spinning disk latency is in the order of 10 milliseconds. That means order of is probably, if you have fast disk, it's probably 5 milliseconds. If you have slow disk, it's probably in the 13 milliseconds. It doesn't matter. It's the order of 10 milliseconds. A flash-based storage is probably in the order of 0.1 millisecond. Again, if you have a fast one, well-engineered, it's probably 5 times less than that. If you have a slow one, bad quality, it's probably 5 times more. It doesn't matter so much. In terms of these pathological cases, it matters into the average which you get, which your users are also, of course, interested in. But the problem is that the IOs are not always in this order of magnitudes. That's what we will see with some examples, and I encourage you to look in your system afterwards. And if they are not in this order of magnitudes, that is 10 times slower or more, like 100 times slower sometimes, then you should know it. Sorry about X marks. That's unexpected. Yeah. You should know because you can actually look at it and you can hopefully reduce that, and we'll see that why. The reasons for having these outliers are primarily bugs in your OS, in your storage subsystem, into ASM. It can also be temporary or global overload. If you would read some of the books about it, there's something called queuing theory, which describe based on the distribution, which is sometimes not easy to choose, but okay, if you pick a Poisson distribution, and then you have a number of entries of changes arriving at the same time, then some of them will be long. The comparison is usually made with supermarkets, that it can go fast, but at some point, for whatever reason, if there's a peak of people coming up, you might have an overload, and then it takes a very long time. So it might happen, it can be a temporary, or it can be a global overload of your system. What matters is that you should know about it, and because you have to correlate it with the OS log, the storage subsystem logs, the ASM logs. Imagine you have a disk failing, that can be a very good reason for having some slow IOs, outliers. And so you would think that normally the Oracle database has information about it. So it has some information, but what I think is that it doesn't have enough. And AWR, the Active Workload Repository, has some information because it captures histogram information, but it doesn't capture really single I/O. You could think that it actually does with the sampling of hash every 10 seconds, but that's not enough. So you don't get enough information out of it. So AWR keeps an history about histograms, about your I/Os, but we'll see that it's not what matters. More addition to that, AWR does not capture information on active data guard because it has to write locally, and as AWR active data guard doesn't write locally, you don't have this information. So you're kind of blind from this information. Actually, you don't even have AWR. So in addition to that, I think it's actually desirable to extract the information for two reasons. One is that you probably don't want to bind it to a given database. You want it to be more global because you want to have a global view about your I/O subsystem. Sometimes it's shared across multiple systems, so it doesn't make sense to have it localized in one specific way. So that's across migrations. You probably want to have it outside of a given database. What you also want is you want to have a very long time. So AWR people, I think the default is 7 days. Many people have it for 30 days, maybe 6 months, but actually in practice for these I/O operations and information, you probably want to go like 18 months or more. So what to do for it? It's very simple. So essentially the database does the hard work for you, you just need to do something very simple afterwards. So active session history is a sampling of database sessions every second. So each horizontal line here is a session. You have some foreground processes, session 1, 2, 3, 4, and you have one of the background processes, log writer. And essentially what you have there is that the sessions are waiting sometimes for something. And what active session history does is that every second it samples and it keeps a trace of what the sessions were. And typically, it's supposed to keep it for 24 hours. Of course, it depends on the activity and things, so you can also change the sizing of it. But okay, imagine you have it for more than 1 hour, which is hopefully the case. What you can do now is that you can run a job on all of your databases. The way I did it is actually I run it centrally. So I have a machine which every 15 minutes connects to all of the databases and fetches the information I want to keep. The information I want to keep is not about each of the wait events. If there was a blockage between two sessions, a TX contention, I'm not interested. What I want is only the ones about the I/Os, and I want only the I/Os which are badly long. So more than, I don't know, 100 milliseconds, 1 second, it depends on your average. So essentially you take your average, you add something, and then you say, that is what is not correct for me, depending on the way you want. Imagine it's you have an average of 5 milliseconds, you might want to say, if the I/O is more than 25 milliseconds, it's actually a bad I/O, I want to know about it. And so essentially by storing all of these long I/Os into a database, very simply, just do an insert from VDOL active session history, or GVDOL active session history. You want to capture the global picture of your access system. And then you insert that into a table. Then on the central database, then you just automatically get a repository of all of the long I/Os. And then you can do query to identify major issues, and what we will be doing now. And you can as well correlate with histograms and the total I/O operations. Because of course it's not the same to have one I/O, which is very, very long among a million, than compared to one among hundreds. So let's look at it with a short demo. So, you see that, yes. So for those of you, that's something called RStudio. It's R, the statistical package, where you can connect to database. In that case, I made a copy of the a part of the repository in order to get information. And then you can just say, I want to do a select and graph the outcome. So let's do that. So this is the number of I/O operations. So it's not each I/O operation, that's a count in that case. Of I/O operations which took more than a second. The good thing why I select 1 second in that case is that if I do 1 second, I'm guaranteed to capture them all, because hash is sampling every second. So I'm guaranteed to have them all. And then I can see that I had, before April, a large number of them, like per day, 10,000. It's a log scale. And then on April, we actually changed that, and it's much better. So why April? Because April was a migration. We went to different subsystems, which has a different type of patterns. So we see the evolution there. Let's do another one where we can do another graph of it. And there, we're not doing a count. We're looking at each individual long IOs, or pathological long IOs. And that's very interesting, because what you see there is that before we were saying, globally there were 100 bad IOs per day, kind of. And then you see that's very different. That's time on the x-axis. And we see that sometimes, at some time of the day, we get a large number of these IOs. Moreover, these IOs are not, I don't have a big chunk of bad IOs at one point. I've actually have them spread horizontally, which means that it's not a timeout. It's actually something which is more a random type of operation. So, as I want to leave enough time for the next person, there's also something I wanted to show you, which is very brief, which is the fact that you can use some systems to actually visually drill down into your IOs and find out. So this tool is called NDECA. It's one of the Oracle products, actually. And the people who I work with are some of them are very good at this data analytics work, and they advise me to look at NDECA. And by the way, so that's a total weighted sum by database. So you see, I have the list of databases. Now I'm changing. I'm saying I want to look at the time weighted, the sum of the time weighted, and there I see that one is actually outstandingly coming there. I should probably stop here. There you see on the right the events, and you see the time weighted by these long IOs globally. Now what I want to do is restrict specifically to one database, this ABCR database in that case, and I want to restrict the time, because imagine I've been told by the user community that something is wrong during that period of time. So I can select and say, please only look at, in that case, part of the month of September. And there I'm restricting the data set. And there I see that log file syncing is coming up there. Log file syncing is not a real IO operation, so I'm actually removing it. That's what I'm doing here. And now, what we're doing is that we see a more balanced, that we see that DB file sequential read, which is this random IO type operation, is coming up. What we want to do first is actually look at in the time when we had these long IOs, and then we can see some patterns which are interesting. Now I will want to actually select only the sequential read. That's what I'm doing on the side. And there, one day pops up as very interesting to look at. So I'm selecting only that day. And then you can even drill down further and look at the sample time. You got the point. I mean, that essentially, if your data is in a database, It's very easy to drill down and find out some of the patterns and then correlate with some other type of information. So that's everything I wanted to tell you. Is you have the information, it's just that you're not collecting it properly. And it's very important for many reasons, for bad cases like bugs at different places of your infrastructure, or for overload which are coming up, and you probably want to do it before it really happens. That's everything I had for today. Thank you.